so would you want to report out those metrics, or what would you communicate in? Would that be for a technical audience, or for a super user, or the public?
I mean, I guess, yes, it could be all of them. I mean, one of the things you could do on a micro data set is actually provide, at least for the sampled cases, what the estimate of the error is from the estimation. So I guess at each domain you could give these types of estimates, and you could, whatever you're estimating being the probability of being correct would also be a good metric, and those would mostly be at these domain levels. And then it's a good practice to know what kind of undercovers the amount of undercovers you're having, and that's directly estimated.
So I could see. Okay, let me stand up. Where do I need to stand?
Oh, you're perfect, wherever you are.
Okay.
It's just we have Scott's slides.
All right. I have a follow-up question, because I think the newspaper reporter might have a bit of trouble. That's a follow-up. But let's do Scott, and then that'd be my question.
Okay. Scott, can you hear me?
Yeah, I can.
I have to drive the slides. Can you just tell me, next slide?
Yeah, I'll just that'll be fine. So I'll just go ahead and get started. I know this one session is about harmonization, and I'm going to talk specifically about spatial and spatiotemporal. Hello, can you hear me? No? No?
Scott, just a second. Can you hear us?
Can you hear me?
We can't hear you, Scott.
I can't even get to the...
Can you hear me? I'm just going to use the speakerphone since it's not working. Can you hear me?
Yeah, now we can.
All right, we'll just go with this then. So what I'm going to do is I'm going to talk about spatial and spatiotemporal change of support, but I'll also highlight some issues that come up in other areas that are related to the topic session here as we go through. But before I do, I want and there's some projects that I'll describe at the end that John didn't work on, but he was the guy.
Scott, we heard before you do and then nothing.
Next slide.
I heard you say before I do, and now I can barely hear. I heard you say sorry, but I'm probably the only one, and that's because I'm right by the speaker.
All right, can you hear me now?
Yes.
Can you hear me now?
Yes.
How about now? Can you hear me now?
Yes.
Okay, perfect. So let's go to the next slide. Okay, so the original motivator for this some of this methodology is the American Community Survey, and certainly the audience is no stranger to that. It's an ongoing survey that's administered by the census, and it provides timely information on many key demographic and socioeconomic variables. Currently, the ACS produces 1 year and 5 year period estimates and corresponding margin of errors for different demographic and socioeconomic variables, and these are recorded over different predefined geographies within the United States. And then, as of I think it was 2013 or 15, I can't remember the exact date, they canceled the 3 year period estimate, and that caused some angst for data users. So there's a couple of different aspects of change of support, and the key aspect of that is producing estimates on multiple scales. So if you wanted to have user-defined geographies and or user-defined time periods, then you could do that with this sort of methodology. So the first example would be something where we have a spatial-only change of support, and we provide estimates on user-defined geographies. But then you could think, okay, so now that the ACS got discontinued and you're a data user, if you were in a geography that really relied heavily on 3 year period estimates, you'd be a little bit upset that your tabulations got canceled. And so you'd say, how do I come up with tabulations for that missing 3-year period estimate. And so this methodology allows you to do that as well. So next slide. Okay, so there's two general approaches to doing spatial change of support. So I'll describe that sort of first. There's a bottom-up, where you estimate the variable at a very fine scale of geography, very fine resolution, and then we call that a source support. So these are the regions that are associated with the data, and then you average the variables up to some sort of target support. So that's the region that you're interested in having estimates on. There's also a top-down approach which people use, which define the process by partitioning the source support and target support. And I put a reference there, this Muglin 1998, but I'm not going to really talk much about top-down type methodology. And there's a lot of good reviews out there, and I'm trying to list some papers along the way, and certainly if people have interest, they can contact me offline. There's a paper, one of the review papers, one of the seminal papers on this is the one that's by Gotway and Linda Young, the person chairing this session, and then there's also one by Weicker and Berliner in 2005. Next slide. Okay, so the spatial change of support problem can be motivated this way. So if you are in like New York City, you want to get estimates, the local government there, the Department of City Planning, does create estimates on what they call community districts. But they don't actually, the community district boundaries, as you can see in the upper left-hand corner for New York City, are not, they're not directly coincided with what happens when you aggregate up the census tract to the New York City PUMAs, the public use micro area. So there's some mismatch, or they're misaligned, and depending on the variable that you're estimating, that could be problematic. So go to the next slide. So in that work that we published in JASA, we did a Bayesian spatial change of support model for count valued survey data. And the reason that that's interesting is because what we do in that paper is we use a Bayesian statistical model, and that incorporates dependencies between different regions. But if you think about, okay, you're going to do this change of support, and you want to account for the sampling error variance that comes in from the direct estimate, then how are you going to do that in a count data setting? And so we developed a method that used the survey variances to improve the quality of the estimates from our model. And this methodology uses a bottom-up approach. Next slide. Okay. So as I mentioned, the Department of City Planning in New York City used that ACS period estimates of poverty, demographic, and social characteristics, and they're interested in obtaining these variables defined in this community district. So that's the target support I mentioned earlier. But instead, they use an aggregate of census tracts. So that's the source support. And since they do that because the ACS is not available on their geography of interest, which is the New York City's community district. So we proposed this spatial change of support methodology to change support of the 2012 5-year period estimates of poverty from census tracts to the community districts. So next slide. So if you look at the poverty by census tract in New York City, you have this plot up in the left, and then you have the associated survey variance, or the sampling error variance associated with the direct estimates by census tract on the right-hand side. And if you look at a scatter plot of the log count versus the log survey error, you can see that there's potentially some over-dispersion. So not handling that extra source of variation when you do a change of support in the Poisson setting could be problematic. Next slide. So our statistical analysis gives a posterior mean and posterior variances of the mean number of people in poverty defined on census tracts, as well as community districts. And you can see this in this bottom slide here, and we have some diagnostic measures in the paper that were used to ensure that the quality of the estimates were reasonable, and I'll let you look at the paper if you have more interest. Next slide. So the next thing that we did is we did space-time change of support. So the literature for spatial change of support is relatively, by comparison, is significantly more mature than the space-time change of support. but we wanted to do something where you could change the support both in space and time. And so this allows people to define their own time period. So you could even conceive of having estimates on periods that don't coincide with tabulations that the Census Bureau releases. So if you wanted to have a 4-year period estimate, you could do that, even though that's not a data product that's currently supported by the ACS. So this allows ACS users to define geographies and time periods that are meaningful to them, and allows one to compare different aerial units by providing estimates on a common time period. So typically ACS users want to compare trends across geographies, and those different geographies could have different period estimates. And so there's not really a coherent way of comparing those trends without doing some sort of change of support. And so this paper's published in STAT, and I'll leave the details there. Next slide. So if you look at the 3-year period estimates of median household income, these are the 2013 ACS estimates along with their corresponding survey standard errors. So you have the 5-year period estimates and the 3-year period estimates and the 1-year period estimates on the left-hand side, and then their associated standard errors. Next slide. And what you can see when you look at these types of plots is that the longer time periods have fewer missing regions, right? So if you have the 1-year period estimates, those are going to be the ones that have the least coverage, and then the ones with the 5-year period estimates have full coverage. Next slide. So in this case, when you look at the ACS estimate of median household income, each period estimate, if you look at the scale on the right-hand side, the color bar, it has a relatively large measure of uncertainty. Okay, next slide. So we do a model-based estimate, so those are the lower plots, G and H, and we use the 1-year period estimates and the 5-year period estimates from the previous slide, but we don't use the 3-year period estimates when creating this. So you can see that you can come up with 3-year period estimates, even though that's not something that's being supported any longer. Next slide. Yeah, the other thing to notice, so we compute ratios of model-based estimates to the holdout 3-year period estimates, and the median ratio was only 1.04, so that indicated the model-based estimates were very close to the holdout. And the other thing that you can see is that the level of uncertainty, if you look at the color bar on the right-hand side for the posterior standard deviation, the uncertainty is much lower with the model-based estimates than using the direct estimates. Next slide. Right, so I already said that. So next slide. So here's a plot of the holdout sample, so the holdout ACS estimates versus the model-based estimates. And these are not on a map. These are just laid out in some arbitrary order. But what you can see is that the model-based estimates are tracking the holdout estimates fairly well. Next slide. Okay, so now you're a data user. This is really important, and you go ahead and you say, okay, I want to change the geography. I want to estimate things on a different spatial support. Then one thing you need to know, is that spatial support meaningful? So there's a potential aggregation error, and this manifests itself. It's called the ecological fallacy or modifiable aerial unit problem. And that's when inference on the aggregate scale of the spatial support differs from inference on another spatial support. And if you look at this plot here, this tiling, you see that like the truth is the one denoted by A, and then B through N are various 2 to 3 group realizations. So if you look at if you look at adding across or adding down, you can see like in B, you add across the top and you add across the bottom, you get something that doesn't look like the truth. And so what you want to do is quantify this error that comes from doing a regionalization, or you may want to select optimal regionalizations that minimize this aggregation error. Next slide. This is another example. If you look at the ACS 5-year period estimates of median household income for 2013 selected over the the states in the Northeast U.S. So you have these panels. The first one up there is the county level ACS 5-year estimate period estimates for median household income. And the bottom one is the state level estimates. If you look at the Southern Virginia counties, then that have low median income, while the Northern Virginia counties have high median income. At the state level, you couldn't see this, and so you see that there's not a homogeneity across scales. And if you're a policymaker or somebody doing some sort of inference with that data, and you're not mindful about that, then you can come to wrong conclusions. Next slide. So, in a paper that we published in JRSSB, we considered regionalizations motivated by mitigating this modifiable aerial unit problem, and we developed statistical theory behind the modifiable aerial unit problem that results in. But I'm not going to go through that here. The results are fairly technical, and they're based on functional principal component decomposition called Karhunen-Loew expansion. But the results motivate our criterion, which we call the criterion for spatial aggregation error, or CAGE. And you can think about that as being the variance of the fine scale process minus the variance of the aggregate scale process. And so, for example, the fine scale process could be the county level median income, and the aggregate level could be the state level median income. Next slide. And so you can come up with some practical conclusions from this work. CAGE allows us to find optimal regionalizations that minimize this modifiable aerial unit problem. And you can evaluate the severity of the modifiable aerial unit problem for a given spatial domain, and you can quantify the uncertainty that is. And also, this would allow a way to do some efficient dimension reduction by choosing the right regionalization. Next slide. So I talked briefly about this spatial and spatiotemporal changes support and this modifiable aerial unit problem and how we develop this CAGE. But the thing that I want to stress here is, if you think about these things in a hierarchical framework, so if you're thinking like from a hierarchical statistical modeling framework, whether you wanted to think Bayesian or not, maybe thinking about it in a Bayesian context might be easier in terms of computation and so forth. But if I want to combine data from multiple sources on different supports, this allows me a mechanism to integrate that data from different supports while accounting for the uncertainty. So I can think about having this as, this change of support as a data model and going through that sort of estimation. And then if I had another quantity of interest or variable of interest, I could condition on that variable where I've changed the support and account for the uncertainty from going from the one level to the other. And so there's some other topics of interest, and those include, like I say, combining data from multiple sources and different sampling techniques. There's been some good recent work. There was recently a review paper by Sharon Lohr and Raghu in Stat Science that gives an overview of that sort of methodology for combining data from multiple sources. There's also recently a NAST panel that looked at combining data from multiple sources from USDA, and that's full of some good information as well. And we combined data from multiple sources in a paper in 2016 in STAT. We used a multivariate spatiotemporal mixed effects model to combine data from the ACS and Laos on employment statistics. And what you find in that case is that you can do better combining the data than you could with either survey alone. And then in Wang et al., in 2011, we combined data. We were estimating crop yield for the National Agricultural Statistics Service, and we combined data from their three surveys, the Agricultural Yield Survey, the Objective Yield Survey, and the December Ag Survey. And then we also brought in some external covariates, and so those references are there. The other thing that's kind of interesting is if you wanted to combine data from different temporal sampling frequencies, so if you have data that you have a response that's measured on a quarterly basis, but then you have a covariate that you want to include that's on a daily basis. And how do you go ahead and make sense of that in a coherent way? And we have two papers on how to combine data from different temporal sampling frequencies. The first one's a discussion paper here in ASMBI, Applied Stochastic Models in Business and Industry. and then the other one's in spatial statistics. And there's plenty of others that do this, but those are just some quick references. And that's all I have. Thank you.
All right. Thank you, Scott, for hanging with us. Let's open the floor up for discussion, and in particular, if you have questions for Scott, I'm not sure. Scott, can you be around this afternoon?
I cannot, unfortunately.
No, not really. What about
what?
Don and Ben? Are you guys going to be here all day? More or less? Okay. So let's be sure and get the questions that we have for Scott, and then I'm only going to allow about 5 minutes for this, so then we'll have questions for Don and Ben as time permits. Anybody have a question